If you are searching on how to solve the slope and deflection of cantilever beams by the moment area method, then this video is for you. As we can observe on this figure, cantilever beams are beams supported with fixed support at one end and overhanging at the other end. What is identical for this kind of beams is the way it will deform when it is loaded downward, regardless of the loads it carries, even if they are combined or applied individually. Here is an example of a cantilever beam with a support located at left end. Before the loads are applied, the neutral axis remains to be horizontal or undeformed. After applying the loads, the beam will respond and the neutral axis will bend. This is also called the elastic curve. Very important theory about the elastic curve of this kind of beam is the way it will bend. From the fixed support, it will have a small horizontal line, then follows a curvilinear path down to the overhanging end. Common problems require the slope theta, theta b, and deflection delta, delta b at the overhanging end of the beam, even if there are also problems where it also asks to determine the slope and deflection anywhere throughout the length of the beam. To solve this problem, we will now analyze the geometry of the elastic curve and the tangents drawn on the curve and find relationships that is equivalent to the two theorems of moment area method that in return can be converted to equations that will solve the problem. It is now important for us to review the theorems of moment area method. The first theorem states that the slope in between two tangents drawn at any 2 points, those are point A and point B respectively in the figure, and the slope in between those two tangents was called theta AB or theta BA, is calculated equal to the area of M over EI diagram or the area under the bending moment curve between the points where the tangents are being drawn divided by the flexure rigidity EI. And the second theorem is about deviation of a point with respect to a tangent drawn at any other point, which is equal to the product of area and a distance. Area is the area of the M over EI diagram or area bounded by the bending moment diagram between the point where the tangent is being drawn and the point where deviation is computed, and a distance which is measured from the center of the area under consideration to the point where deviation is being computed. Going back to our elastic curve, since we have a small horizontal line at the support at point A, before it will deform downward, the slope of tangent line that can be drawn at that point is a horizontal line with a zero slope, since tangent lines are the lines that are drawn just to touch the curve at that point. If we will extend the tangent line at the end of the beam until it will intersect the tangent at the support, which is tangent at A, we can have a slope in between two tangents, theta AB, that can be easily obtained from the first theorem of moment area method, since from the geometry, we can simply prove that the slope of tangent line at B is equal to the slope defined by the first theorem of moment area method. If the area of M over EI diagram is triangular, this is in the case of concentrated load applied at the overhanging end, the slope is equal to the area between A and B and can be simply obtained from the area of a triangle equal to 1/2 of base times height, where the base is L, the total length of the beam, and height is the maximum ordinate of the bending moment diagram, P multiplied by L. Then area is equal to 1/2 of L times PL, which is equal to PL squared all over twice of EI. In the case of uniform load over the entire length of the beam, the area of M over EI diagram under a spandrel of a second degree curve is 1/3 of base times height, where the base is L, the total length of the beam, and height is the maximum ordinate of the bending moment diagram, which is equal to WL squared all over 2. Then area is equal to 1/3 of L, the base, and WL squared over 2, the maximum ordinate, will be equal to WL cubed all over 6 EI. For the deflection at the overhanging end, we will analyze once again the geometry of the elastic curve. We can observe here that from reference tangent at A to the final location of point B in the elastic curve is a change in elevation that can be solved by applying the second theorem of moment area method, which states that the distance from a reference tangent to the final location of the point is equal to the deviation, which can be solved by taking the product of area and a distance which is defined before. We will now solve for delta B, which is equal to the deviation of point B with respect to a tangent drawn at A, which is equal to area multiplied by the distance. In the case of concentrated load applied at the overhanging end, the area, which is already computed before, equal to PL squared all over 2, is multiplied by a distance, which is from the center of triangle, it is equal to twice of L all over 3. Area multiplied by the distance is now equal to PL cubed divided by 3EI. In the case of uniform load applied over the entire length of the beam, area is equal to WL cubed all over 6, and the distance measured from the center of area up to point B is equal to thrice of L all over 4. We can now solve the deflection at the overhanging end, which is equal to delta B, which is from the second theorem of moment area method, that is deviation of point B with respect to a tangent drawn at A, which is equal to area multiplied by distance, WL cubed all over 6EI times distance 3L all over 4. The deflection at point B for a uniform load applied over the entire length of the beam is equal now to WL raised to 4 divided by 8EI. For a cantilever beam which is under the action of a concentrated load at the overhanging end and a uniform load which is applied over its entire length, the total deflection at the overhanging end is equal to PL cubed all over thrice EI plus WL raised to 4 all over 8EI. And for the slope at the overhanging end, that is equal to PL squared all over twice EI plus WL cubed all over 6EI. Therefore, slope and deflection of cantilever beams can be easily obtained using the moment area method. We just have to strive to find a way in order to calculate accurately the areas and centroid of the M over EI diagram.